Our next talk
Yeah, it's still me.
will be given by Francesco again.
Just give me 1 second that I change slide. All right.
And it will be about effectful program distancing.
Okay,
Please, Francesco, go ahead.
Thank you. So second round. So if you were at the previous talk, there we discussed a lot about program equivalence, which is pervasive notions in programming language theory. But if you think about fields like probabilistic programming or differential privacy, it is not hard to realize that sometimes program equivalence can be too strong, because, for instance, it can just discriminate programs that differs just for really small probabilistic behaviors. And for that reason, researchers have started to investigate, or actually to move from notions of program equivalence to notions of program metrics, which now the idea is that instead of saying that two programs are just equivalent or not, you numerically quantify the difference between the programs. And if you're present at previous talk, then you can recognize also from the notation that this sort of quantitative reasoning is in the scope of co-effectful reasoning. But I will not talk about that in this talk. So theory of program metrics, and these have been developed and successfully applied. They give rise to nice compositional theory of program distances, and also to interesting applications, both, for instance, in probabilistic programming and also in differential privacy. But nonetheless, this theory of program metrics has a major weakness, namely that they are context agnostic and in a way non-interactive. And what do I mean by that? Well, I mean that when it comes to quantify differences between programs, then metrics do not take into account the context in which programs are executed. So for instance, to give you a concrete example, so here in the slide, there are the graphs of two functions. The first one is the square of the inverse square root function, which is the black one. And this is an expensive function to compute. But people in machine learning and approximate computing, which I will talk to you about in the next slide, I think, have noticed that if you pass to this function suitable input, which I think that it should belong to the interval between 0.5 and 1, I think, you can reasonably approximate the output of the inverse square root function with a linear function, which is less expensive to compute. And therefore, what we would like to have is semantic notions that allow us to capture this behavior. So that, for instance, that they tell us that the distance between these two functions is small on some specific inputs, and otherwise it is large. But that's not the case. That's not the case, because if you take any theory of program metrics you can find in the literature, but even if you move to mathematics and you take the distance, the metric space that one is considered on function spaces, then you see that the distance between function is computed by taking, let's say, the worst case, or independently on the input. You just pass to the function all possible input, you measure the distance between the output, and then you take the supremum. So it's a really context agnostic and worst case way to define distances between two functions. And in particular, if you use this definition, you immediately see that you are bound to conclude, you're forced to conclude that the distance between the two functions, the inverse square root function and its linear approximation, is infinity. So we cannot rely on program metrics to capture these sort of behaviors. And you may wonder at this point, why do we want to do that? Because I showed you kind of specific example that may look like an ad hoc one for the goal of this talk. So the question is, why should we consider context-dependent distances and interactive ones? And the answer is that this sort of reasoning appears quite natural in several fields. So differential privacy and information flow, for instance, but also adaptive cost analysis, where you want to measure the efficiency of your programs in specific context depending on the input you pass to those programs. And another field which I will use as a running example for this talk, which is approximate computing. When one moves from the simple observation that there is a trade-off between the precision of the results and the resources needed to compute that result. And therefore, what one can do is sometimes to just reduce the precision or the accuracy of the results, and this way gaining new resources. And that turns out to be useful in fields like gaming, computer vision, machine learning, and all these fields in which you don't need to have exact results of computation and you have massive numerical computations. Okay, so that was just talkie-talkie, let's say. So let us see a concrete example of this idea of approximate computing and how it is relevant, let's say, from a semantic perspective. So here we consider the problem of computing the integral of a function over an interval, or a finite interval. And a standard way to do that is to split the interval into a lot of sub-intervals, compute the functions there, and then average the result. Now, suppose now that we want to compute the integral function of the inverse square root functions, and we are not interested in having a super accurate result, but actually in having an efficient one. So we can start to do some approximation of the results, and that makes the computation more efficient. So the first one we can do is that whenever we look at the subintervals, and we see that whenever we have the right input, so to say, we can replace the inverse square root function with its linear approximation. That, of course, will decrease the accuracy of the result, but will also allow us to gain efficiency in computation. And the second approximation that we can do is the so-called loop perforation, which is based on the following idea. So suppose that your n is large, so you have a lot of intervals. Then instead of computing the function on each intervals, you can just randomly select some of them and compute the intervals over there. And that's a good way to somehow, how can I say that? To reduce the complexity of your programs, right? And you see here in the slides where how can you implement this idea. So now instead of computing a function on each xi, you first randomly select some of them and you compute the function just on those. So obviously, if you take the original program and these, let's say, perforated programs, they are not equivalent, right? So what you want to say now is that they are that on some specific input and in some specific context, they are almost the same, or the error is negligible. And as we have argued, the theory of program metrics cannot help you to do that. And for that reason, people have started to, sorry, I missed a slide. Okay, and for that reason, people have started to investigate a richer notion of distances. And in particular, in Bologna, we are working on a theory of higher order program distances. And these theories move from the common observation that the distance between two programs cannot be a number, but it must be something more complex, something that reflects the interactive complexity of programs. And in particular, in this talk, I will focus on differential logical relations, which is one theory of higher order program distances, which somehow extends the theory of metric logical relations. Metric logical relations, you just have a numerical distance between programs, whereas in differential logical relations, you take distance between programs to be richer objects that depends on the type of the program, and so from its interactive complexity. And the main construction is the one of distances between functions, or more generally, distances between programs of a narrow type. In that case, you say that the distance between two functions is itself a function, so it's a complex object that takes as input the original program, a distance or a perturbation, if you like, on the input, and it produces a perturbation in the output. And in this way, you see that distances becomes higher order objects themselves. Okay, this is all very nice, but there is just one problem, namely that all the theory of higher order program distances that you see here in the slide works for pure programs only. And that means that it cannot be used to reason to perform semantic reasoning about the examples that we have seen before. And that's essentially a contribution of our work, namely the development of a theory of effectful higher order program distances. And in particular, we have developed effectful differential logical relations, which are the extensions of differential logical relations to languages with computational effects. We give it a semantic foundations for them, and we've also studied applications of the theory to fields like probabilistic approximate computing, cost analysis, and differential privacy. Okay, so let me outline the main technical development behind that contribution, starting with generalized distance spaces, which are the very basic elements of the semantic foundations of our theory of effectful higher order distances. So what is a generalized distance space? Well, it's just a set together with a set of distances for elements in that set. So notice that distances are not fixed once and for all as numbers, let's say, but they change as long as the underlying set changes. And all of that is endowed with a ternary relation that tell us, given two elements, what is a distance between them. So a couple of examples. So if you take the real numbers, well, here there is essentially no interactive complexity. So as a generalized distance space, you can take the one that essentially originates from Euclidean distance. So distances are just non-negative real numbers, and the ternary relation is just given by the Euclidean distance. Now, in the interesting case comes when you move to more complex sets. So in particular, we can form the exponential of generalized distance spaces. So if you have two distance spaces, A and B, let's say, we can build a distance space for functions from A to B. And such a distance space will have distances, well, mimic the one that we have seen for differential logical relation. So a distance is itself a function that takes an input, a distance in the input, and returns a distance in the output. And the ternary relation now tells us that the function df is a distance between two functions f and g. If whenever you pick two input and the distance between that input, then by giving the distance and the input to df, so to the distance between the two functions, you can compute a distance between the output of the two functions. All right. And generalized distance spaces forms a category where arrows are given by ordinary functions plus differential functions, which are a way to mimic the constructions of exponential of generalized distance spaces. Well, actually, one should do the opposite. So first defining arrows and then defining exponential, mimicking the structure. But I guess you got the point. And this category is Cartesian, closed, so it has nice properties and so on and so forth. But the point is, where are effects? So we model effects using monads, so as customary. So we can use the distribution monad to model probabilistic effects, the writer monad to model output, and also the cost monad to model the cost of computation. So we can also capture some intentional properties of programs by means of effects in a way. And now the main question is, what is the distance between monadic values? Now, if we think about previous constructions on generalized distance spaces, well, we have seen that the distance between two numbers is a number. The distance between two functions is a function, although of a different kind. And so it is natural to guess that the distance between two monadic values is a monadic distance. And that sounds reasonable. So for instance, it sounds nice to say that a distance between two distributions is a distribution of distances. So for instance, if you're familiar with literature on coupling and optimal transport, well, that idea fits this definition. However, if you think about other effects, like for instance, the writer monad, well, then this definition tells you that the distance between two computations with output strings is a distance with an output string, so which is like saying that a difference between two output strings is itself a string, which does not sound quite right. So how can we fix this problem? Well, the solution that we have found was to essentially change the point of view. So instead of giving an explicit definition of what is a monadic distance, we have isolated some structural condition that defines what are somehow the minimal requirements for qualified as a monadic distance. And in doing so, we have introduced the notion of a differential extension of a monad, which is a construction on generalized distance spaces that, given a space on a set A, construct a generalized distance space over T of A, where T is the monad we are interested in. And of course, this construction has to satisfy some specific properties. In particular, it must come with differential extensions of the unit of the monad and of the bind of the monad, which amounts to say that you can extend the unit and the multiplication of the monad to arrows in the category of generalized distance spaces. And these constructions can actually model the several examples. So for instance, in the probabilistic case, then you can stipulate the distance between two distributions is a ternary distributions, and in particular ternary coupling. So again, if you're familiar with optimal transport, coupling, and literature in general on probabilistic metric spaces, well, our notion of a differential extension can be seen as an extension of those ideas to a higher order setting. Whereas if you now take the Ryder monad, then we can take as a differential as monadic distances natural numbers together with distances. And in that case, the natural number gives you an approximation of the least common prefix distance between the strings produced as output, for instance. All right, so now that we have a semantic foundation, let us see how we can apply them to a concrete calculus, and this way defining differential logical relations. So what we have done was to study call by value lambda calculus, reached with algebraic operations and monads. So that's the way in which we model algebraic effects. And we have defined effectful differential logical relations as an operationally based semantics for this calculus in the category of generalized distance spaces. And in particular, we have defined two generalized distance spaces, one for terms and one for values, relying on the construction that we have seen in previous slides. So in particular, the generalized distance spaces for values of an arrow type are constructed as an exponential object, whereas the generalized distance spaces for programs, so for objects that produce effects and has to be evaluated, are defined relying on the differential extensions of a monad. And the main theorem that we have proved is that the notion of a differential extension is precisely what one needs to extend the so-called fundamental lemma of differential logical relations to an effectful setting. And that lemma states that for any program T, there exists a self-difference for that term. And what does that mean? Well, operationally, it means that we can reason about higher order distances between programs in a compositional way. So suppose that you have, you want to measure the distance between compound systems. How can you do that? Well, you can just decouple some of the systems, reasoning about the distance between, let's say, the inner component T and S in the slides here, and you can do that in isolation. And on the other hand, you reason about the distance between the self-distance between the context in which you put these two programs. And that self-distance tells you how the context modifies, how the context acts on the input distances. And yet this analysis is decoupled. So you can do that the one for the context, you do that once and for all, independently of the input that you pass down. Okay, let me conclude with a concrete example of that. So remember our motivating programs. So the one for computing the integral of a function, which I called P here, and its loop perforated version or approximation S here. So suppose now that we have performed this approximation and we want to replace the original program with the perforated one inside the context C that you see here in the bottom part of the slide. Well, what you do is you compute the self-distance for this context, and the fundamental lemma tells you that you can always do that. And here in the bottom part of the slide, you see a self-distance for the context. That looks scary, but actually, if you play a bit with types, it's kind of easy to compute that. And once you have that, and once you have calculated the distance between T and S, you can just pass T and that distance to the self-distance for C, and you can compute the overall distance between C of T and C of S. And by the way, what is the distance between T and S? Okay, now we know the distance for the context. What about T and S? Well, if you look in the paper, there we explain how you can compute them. But if you trust me, you can see that if you pick this formula here in the bottom part of the slide, then you can prove that the term T and its perforated version S are in the differential logical relations with this distance here. And that means that we have obtained a full differential analysis of this program and its probabilistically loop perforated version. Okay, so concluding, what I show you is the theory of effectful differential logical relations and its semantic foundations. And more generally, I showed you how to use them as a sort of as a possible theory of higher order effectful distances. What I haven't shown you, but this is something that you can find in the paper, are applications. So we have just sketched one application to probabilistic approximate computing. But in the paper, we also show application to cost analysis, in particular to relational cost analysis and adaptive complexity, and also applications to differential privacy, where we show how one can use effectful differential logical relations to define the notion of expected higher order program sensitivity. Okay, that's all for this talk. And again, if you have questions, please go ahead.
All right, let's thank Francesco again. Any question from people in the room? We have one question online. Very interesting talk. Do you think it will be a lot of effort to extend this work for the effectful, co-effectful setting?
Well, that's a very good question. So on one hand, what we are observing is that several co-effectful analyses can be given using differential logical relations, mostly with effects, but some of them even without effects. So in that way, you can see differential logical relation as a way to somehow incorporating co-effects. On the other hand, you could, well, just say, okay, I start with a language that has both effects and co-effects. And in that case, I guess that what one should do is to come up with differential extensions of a comonad. However, in that case, well, even understanding what kind of relation one should use is not super clear. Maybe quaternary relation. We haven't really think about that. So we have thought a lot how to incorporate a co-effectful analysis in a differential setting, but not to extend differential setting in the co-effectful one. So I don't have a precise answer to your question, but that's something interesting, and we should reflect about that.
Okay, time for another question. Anybody has a question? If not, I have a question actually. So you show us that mainly when you were lifting, let's say, the relation to probabilistic computation, you told us that it was a generalization of coupling. So usually in traditional lifting, we have different way of doing the lifting. I imagine that here by adding an extra parameter, the theory become even richer in the sense that probably there are multiple ways to build that lifting. Is my understanding correct? Did you look into this?
Possibly, we haven't really looked into that. So what we have done was, well, first defining this ternary coupling, but then we have also recovered this definition in the more general setting of a monad preserving weak fullbacks. And what we have done was essentially to extend bar constructions to this setting of ternary relation. So in this sense, I guess it is somehow canonical. But you're right that when you look at the probabilistic case, you can consider variations of that lifting, and we haven't thought about that. So my guess is that the lifting remains the same. The point is that what you can do with this lifting, because now that you have this term recoupling, then you can extract numerical information out of it, taking, for instance, the expectation or taking kind of value passing expectation. So maybe you can recover different notions of coupling by changing that map. So instead of taking the expectation, you may take some weighted version of it or something like that. But I'm not entirely sure of what I'm saying. So again, this is something we should look into that.
Okay, thanks. Time for one very last question. If not, let's thank Francesco again.
Thank you.